Hi everyone! This video is part 12 of roll center and comprehensively examine load transfer distribution according to roll center height and roll axis inclination and examine their impact on handling performance. Both size and time are important factors in load transfer distribution. As discussed in the previous videos, load transfer ratios vary depending on roll stiffness, and roll center height also affects the load transfer ratio. Load transfer due to roll stiffness and load transfer due to roll center height have different speeds. We'll analyze the behavior of a vehicle performing a transient turn-in to understand the effects and sequence of these two load transfers. Some argue that a lower roll center increases roll moment and thus load transfer. Others argue that understeer characteristics are induced when the roll axis inclination is lower at the front and higher at the rear. Let's examine whether these two opinions are correct. If you found this video helpful, please hit the thumbs up and catch the brand new videos by free subscription. Also turn on alarms to be the first to enjoy new videos. Let me introduce the content of this video. This video builds on the load transfer distribution discussed in the previous video and explains how it affects handling. In the idealized spring model, the load of the sprung mass is transferred in two ways. The first is the moment produced by the sprung mass under lateral acceleration about the roll center, which is transferred through the spring, anti-roll bar, and shock absorber. In this case, the load transfer occurs differently at the front and rear wheels, depending on the ratio of the front and rear roll stiffnesses. The second is the load transfer caused by the lateral load acting directly on the roll center, which is transferred through the suspension links. In this case, the load transfer occurs differently at the front and rear wheels, depending on the roll center height. The load transfer of the unsprung mass is proportional to the height of the center of unsprung mass. Since the load transfer due to the unsprung mass has been fully explained in the previous video, it will not be discussed further in this video. I have a quiz for you. Which of the following has the fastest load transfer speed when steering a vehicle? Number 1. Load transfer by spring. Number 2. Load transfer by shock absorber. Number 3. Load transfer by suspension links. Number 4. The load transfer speed is the same in all of the above cases. Please choose one of these four. First, let's review the overall load transfer of the sprung mass under lateral acceleration. In the previous video, E0077, roll center part 9, we understood that if the sprung mass is rigid, the front and rear roll angles are equal. We then saw that, during a steady-state vehicle turn, the lateral forces acting on each sprung mass center produce different moments about the front and rear roll centers respectively, proportional to their own suspension roll stiffnesses. Therefore, these different moments produce different load transfers to the front and rear respectively, and consequently, the ratio of front and rear suspension load transfers affects handling. These load transfers are transmitted through the springs and anti-roll bars. I explained that, all other things being equal, the side with the higher suspension stiffness experiences a greater load transfer, resulting in either understeer or oversteer. The mathematical expressions for these load transfers can be expressed in the first terms of equation 1 and equation 2, shown in green. However, if the front and rear roll center heights are different, the suspension roll stiffness alone cannot determine the handling characteristics. This is because the lateral force acting on the sprung mass directly acts laterally on the roll center, producing a greater lateral load transfer through the suspension links on the side with a higher roll center than on the side with a lower roll center. This can be expressed mathematically as the second terms of equation 1 and equation 2. Each of the second terms indicates that the load transfer caused by the lateral force acting directly on the roll center by the sprung mass is proportional to the height of each roll center. In practical applications, both of these effects must be considered. Additionally, as shown in the third terms in equation 1 and 2, there are load transfers caused by the lateral forces acting on the unsprung masses, but since they are not related to the roll center, it will not be considered here. This figure shows the front and rear roll center heights together to explain the relationship between roll center height and load transfer distribution. For ease of explanation, the roll center is assumed to be located on the central longitudinal plane. Assuming the front and rear sprung mass centers are equal, we will explain the movements of the sprung mass centers due to roll motion. First, let's explain the figures. The upper left figure shows a rear view of a vehicle turning left. Pi represents the roll angle, MSR represents the rear sprung mass, and MSF represents the front sprung mass. RCR represents the rear suspension roll center, and RCF represents the front suspension roll center. Furthermore, HRCR represents the height of the rear suspension roll center, and HRCF represents the height of the front suspension roll center. Here, HR represents the distance from the rear sprung mass center to the rear suspension roll center, and HF represents the distance from the front sprung mass center to the front suspension roll center. Also, FIY represents the lateral force acting on the inner wheel, FOY represents the lateral force acting on the outer wheel, FIZ represents the vertical force acting on the inner wheel, and FOZ represents the vertical force acting on the outer wheel. Delta FTL represents the amount of load transfer. The figure on the upper left shows the heights and lateral positions of the centers of the front and rear sprung masses when a rigid sprung mass rolls. If the sprung mass is defined as a rigid body, then when the sprung mass rolls, the roll angle phi of the sprung mass in the front suspension is equal to the roll angle phi of the sprung mass in the rear suspension. Accordingly, since the roll angles are equal at the front and rear, the corresponding sprung mass center shift outward more on the side with a longer distance from the roll center to the mass center than on the side with a shorter distance from the roll center to the mass center. In this figure, the rear sprung mass center shifts outward by a distance dr, while the front sprung mass center shifts outward by a distance df. As shown in the upper left figure, when the distance between the sprung mass center and the roll center is greater, the sprung mass center relatively moves outward more when a roll motion occurs. This slightly increases the load transfer in the case of the greater distance. The load transfer, due to the lateral movement of the sprung mass center, is relatively small, less than 3% of the total load transfer, so it does not have a significant effect on handling performance. The roll axis of the vehicle is shown in a side view at the bottom. The roll axis is the axis that connects the front and rear roll centers. The front roll center is typically lower than the rear roll center, and the roll axis inclination angle in a typical vehicle ranges from 6 to 12 degrees, as shown in the figure below. Let's examine the load transfer distribution based on the roll moment produced by the forces acting at the sprung mass centers about the roll centers. The roll moments of the forces acting at the sprung mass centers can be expressed by the equation 3, which is the first term of equation 1 for the front suspension, and by the equation 4, which is the first term of equation 2 for rear suspension. In the previous video, we assumed the sprung mass to be a rigid body, and that the roll angles of the front and rear suspensions are equal. If the front and rear roll angles are equal, the side with the greater roll stiffness will experience greater load transfer. Therefore, if the front suspension roll stiffness, K pi F, is greater than the rear suspension roll stiffness, K pi R, the proportion of load transfer to the front wheel increases. If the rear suspension roll stiffness, K pi R, is greater than the front suspension roll stiffness, K pi F, the proportion of load transfer to the rear wheel increases. As the load transfer increases, the normal load acting on the tire increases. As seen in the previous video, as the normal load on the tire increases, the coefficient of friction decreases, so the external force that the tire can withstand in the horizontal direction increases by a smaller amount than the increase in normal load. Accordingly, when the speed increases during a same radius turn and the lateral force increases, sliding occurs first on the side with greater load transfer. Since the roll angle phi of the sprung mass, caused by the lateral force, is the same on the front and rear axles, when the sprung mass rolls, the side where the sprung mass center is farther away from the roll center will move outward more than the side where it is closer. Therefore, at the roll center position shown in this figure, the front mass center will move outward more than the rear mass center. As the distance that the sprung mass center moves outward increases, the load transfer increases because the sprung mass center moves closer to the outer wheel. In this way, if only the lateral movement of the sprung mass center is considered, the load transfer will be greater on the side with the longer distance from the roll center to the mass center. However, this effect is less than 3% of the total load transfer in most vehicles, which is not much larger than the load transfer caused by the sprung mass about the roll center as discussed above, and can be ignored when judging handling performance. The picture here is exaggerated to help you understand, and it does not occur to this extent in an actual vehicle. This time, we will look at roll center height and load transfer distribution. As explained earlier, the roll center height determines the amount of lateral load transferred through the suspension links and the amount of lateral load transferred through the springs. Since we have already discussed the load transfer through the springs, let's now look at the load transfer that the lateral force acting on the sprung mass directly produces laterally at the roll center. This load transfer is transmitted through the suspension links, not the springs or anti-roll bars. The amount of load transfer through the links is determined by the magnitude of the lateral force acting laterally directly at the roll center and roll center height. The amount of load transferred through the links for the front suspension can be expressed by the second term of equation 1, equation 5, and the amount of load transferred through the links for the rear suspension can be expressed by the second term of equation 2, equation 6. As shown in equations 5 and 6, the amount of load transferred through the suspension links increases in proportion to the roll center height. Therefore, if the roll center is higher on one side, the proportion of load transferred through the suspension links on the higher side is greater, and the proportion of load transferred through the suspension links on the lower side is smaller. The roll center of the early wishbone suspension was designed to be in the same position as the ground, but the roll center height of most vehicles on the market today is between 50 and 200 millimeters. Let's look at the concept of swing center in wheel movement. This figure shows how the location of the wheel contact point with the road changes laterally as the wheel moves up and down during bump and rebound. Here, point S represents the swing center of the right wheel. The vehicle's wheel moves in a circle around the swing center instantly at a bump or rebound. The tire road contact point is originally R0, but at a bump, the tire road contact point moves to R2, and at a rebound, the tire road contact point moves to R1. This vertical movement of the wheel is accompanied by lateral movement, and as a result, the wheel track changes in the order just described, T0, T2, T1. If the track change is severe, at a bump or rebound, a lateral reaction force is produced in the tire, which increases the shear stress and increases tire wear. In the early development stage of the wishbone suspension, the roll center was positioned at the same height as the road surface in order to minimize the lateral force produced in the tire due to the vertical movement of the wheel. However, if the roll center is at ground level All load transfer is done through the spring and anti-roll bar, not the suspension links, so even if the lateral acceleration is small, a relatively excessive roll angle will occur. In addition, since the suspension links have no force to support the sprung weight, the probability of the vehicle's bottom contacting the road increases even with relatively small lateral acceleration. Increasing roll stiffness to prevent excessive roll angles can lead to a deterioration in ride quality. Therefore, the roll center height of vehicles currently on the market is not on the ground and is determined by compromising to balance the overall vehicle performance, such as ride comfort, underbody clearance, and handling. Let's look at the relationship between roll center height and scrub rate. During a bump or rebound, the tire and road contact point, R, moves perpendicular to a line connecting points S and R. Centered at point S, scrub rate is defined as the rate of lateral position change of the point R during a bump or rebound. In the figure here, the tangent of the angle between the tangent direction of the circular motion of the tire road contact point R around the swing center and the vertical line is the rate of change of the lateral position of point R. Therefore, scrub rate can be expressed using line segment lengths TR and TP as shown in equation 7. Since triangles SQR and PTR are similar, this value can be expressed using line segment lengths QR and QS as shown in equation 8. All of these can be expressed in a single equation as shown in equation 9. From the figure here, we can see that as the swing center increases, the roll center also increases and the scrub rate increases. As the scrub rate increases, the lateral movement of the tire during bumps and rebounds increases, resulting in increased lateral forces and, consequently, increased tire wear. Let's look at the relationship between suspension geometry and scrub rate. As previously explained, the vertical movement of the wheel during a bump or rebound inevitably involves a change in the wheel track. Figure A illustrates a case where the swing center is formed toward the inside of the vehicle. Generally, when the swing center is formed toward the inside of the vehicle, the roll center is located upward from the ground, which is called positive swing arm geometry. On the other hand, as shown in figure B, when the swing center is formed toward the outside of the vehicle, the roll center is located downward from the ground, which is called negative swing arm geometry. As a special case, when the upper arm and lower arm are parallel, the swing center intersects the road surface at infinity, so the roll center is located where the vehicle's central longitudinal plane meets the road surface. As explained in the previous video, as the lateral force increases, the roll center approaches the line connecting the swing center and the road contact point of the outer wheel, where the relatively greater force is applied. Let's look at the relationship between roll center height and load transfer distribution. A higher roll center increases load transfer through the suspension links, while a lower roll center increases load transfer through the springs. Regarding load transfer through the springs and anti-roll bars, as explained in the previous video, we know that the load transfer ratio increases on the side with higher roll stiffness and decreases on the side with lower roll stiffness. On the other hand, the load transfer ratio through the suspension links increases on the side with higher roll center and decreases on the side with lower roll center. Therefore, until we know all of these effects, we cannot determine which side is responsible for the overall increase in load transfer. Consequently, knowing all of these effects together is essential to predicting the handling effect due to the overall load transfer during roll motion. The common misconception that a lower roll center leads to a proportional increase in load transfer is misguided. This belief stems from the fact that a larger distance between the roll center and the sprung mass center increases the roll moment produced by the force acting at the sprung mass center, shifting the sprung mass center outward. However, this belief is incorrect. Let's explore why. Let's look at two load transfers generated by a sprung mass subjected to lateral acceleration. The first is the load transfer caused by the roll moment produced by the lateral force acting on the sprung mass center about the roll center, and the second is the load transfer caused by the lateral force acting on the sprung mass center acting directly laterally to the roll center. Let's look at both of these simultaneously. First, the load transfer of the front suspension caused by the roll moment generated by the lateral force acting on the sprung mass center about the roll center can be expressed by equation 3, and the load transfer of the rear suspension can be expressed by equation 4. The numerator of equation 3 is equal to the front lateral force FSF multiplied by the height HF from the front roll center to the front mass center, and the numerator of equation 4 is equal to the rear lateral force FSR multiplied by the height HR from the rear roll center to the rear mass center. Therefore, it is true that when HF increases, the numerator of equation 3 increases, increasing the load transfer in the front suspension, and when HR increases, the numerator of equation 4 increases, increasing the load transfer in the rear suspension. However, as HF increases, the roll center HRCF of the front suspension decreases, so the load transfer through the links of the front suspension, represented by equation 5, decreases, and as equation HR increases, the roll center HRCR of the rear suspension decreases, so the load transfer through the links of the rear suspension, represented by equation 6, decreases. Therefore, when the values of equations 3 and 4, which represent the load transfer through the spring and anti-roll bar, increase, the values of equations 5 and 6, which represent the load transfer through the suspension links, decrease, and conversely, when the values of equations 3 and 4 decrease, the values of equations 5 and 6 increase. Therefore, it is true that when a vehicle rolls, the load transfer increases slightly because the center of the sprung mass shifts outward. However, the contribution of the shift of the center of sprung mass is so small, less than 3% of the total load transfer, that this alone cannot explain the handling characteristics. Let's analyze the effect of roll axis inclination on handling performance. The belief that a low roll center increases load transfer, and thus affects handling performance, creates another myth that a roll axis with lower front end is necessary to induce understeer. It is true that most vehicles have a lower front roll center than the rear, leading to an understeer tendency. However, a forward tilt of the roll axis does not necessarily lead to understeer. In fact, rather, contrary to this belief, a high rear roll center can lead to a tendency toward oversteer. This can be mitigated by increasing the front wheel load, or by utilizing the camber angle created by the suspension links due to the roll of the sprung mass. Increasing the front wheel load reduces the friction coefficient of the front wheels, thereby reducing the tendency toward oversteer. Furthermore, by increasing the camber angle of the outer wheel, due to the roll of the sprung mass, the camber thrust of the outer wheel can be utilized to support relatively large lateral forces with low tire slip angles. This video briefly examines the principles behind this. Let's look at the change in camber angle due to the roll motion of the sprung mass. As the geometry of the suspension links changes due to the roll motion of the sprung mass, the camber angle of the wheel changes. Let's take a quick look at this. The figure on the left shows the rear view of the suspension link layout when driving straight, while the figure on the right shows the geometry of the suspension links changing during a left turn due to the roll motion of the sprung mass, resulting in a changed wheel angle relative to the ground from a rear view. In the wishbone suspensions, the upper arm is typically designed to be shorter than the lower arm. This design creates a negative camber angle when the wheel moves closer to the sprung mass. As the vehicle turns, the outer wheel moves closer to the body, creating a negative camber angle at the outer wheel. This negative camber angle at the outer wheel provides camber thrust when the vehicle turns, allowing the same lateral force to be supported with a smaller tire slip angle compared to a vehicle without a negative camber angle. Let's find out the relationship between roll center height and handling performance. The left figure shows the case where the roll center is high, and the right figure shows the case where the roll center is low. When the roll center is high and close to the sprung mass center, the angle theta O of the force, FOA acting through the link, will have a large value. Therefore, when the roll center is high, the sprung mass will hardly roll under a large lateral acceleration, and the jacking force will increase, pushing the roll center and sprung mass upward, so the angle theta O will become larger, and the load transfer through the link can increase dramatically. In severe cases, the inner tire will lift off the ground, so all the force will act through the outer tire. This phenomenon can be improved by lowering the road roll center, but this will increase the roll of the sprung mass. To suppress the roll of the sprung mass, the roll stiffness must be increased by increasing the stiffness of the spring and the anti-roll bar. However, increasing the roll stiffness will worsen the ride quality, so it is important to locate the roll center in an appropriate location. This time, we will learn about load transfer in transient movement, where the lateral acceleration is not constant and varies over time. This diagram illustrates all the components involved in the load transfer of a coupled torsion beam axle. The shock absorber, 2, and spring, 3, are the load paths through which the load produced by the roll motion of the sprung mass passes. The suspension link, 1, represents the path through which the lateral force of the sprung mass is directly transferred through the roll center. Finally, number 4 is the path through which the load is transferred by the unsprung mass. In transient vehicle behavior, rather than steady state, the suspension links and the unsprung mass are the systems that transfer the load the fastest. Next is the shock absorber, which damps the moment produced by the sprung mass about the roll center, and lastly, the components that contribute to the load transfer the latest are the spring and anti-roll bar. A shock absorber doesn't work in a state. The same can be said for wishbone suspension. Let's look at how these load transfer times can be applied, for example, when entering a highway by turning in. The turn-in motion of a vehicle is a transient motion, not a steady state. In the steady state, the lateral acceleration is constant, but in the transient state, the lateral acceleration is not constant. Let's analyze the various forces and their action times that occur in transient turn-in behavior. When turning into a highway, a transient vehicle behavior occurs, with steering accompanied by acceleration. The suspensions typically found in street cars are designed with a low front roll center and high front roll stiffness, while the rear roll center is high and the rear roll stiffness is relatively low. First, the force passing through the links of the FOA and the force passing through the unsprung mass are transferred from the tires. Since the force is not yet transferred through the shock absorber and spring, the load transfer increases in the rear where the roll center is high, reducing the understeer tendency of the vehicle. Accordingly, in the initial steering time range, the understeer tendency is less compared to a steady state turning, so the vehicle turns in smoothly. If the initial understeer is still large, the understeer tendency can be reduced by increasing the damping of the rear shock absorber. The shock absorber's response speed is slower than the link, but faster than the spring and anti-roll bar. By reducing the initial understeer in this way, after the initial turn-in, the moment M adds the force through the spring and anti-roll bar, which maximizes the load transfer. After the initial turn-in, at the middle of the turn-in, when all load transfer elements are at their maximum, the vehicle's transient behavior tends to understeer, because the front load transfer is greater than the rear load transfer. Let's find the answer to the quiz. Which of the following has the fastest load transfer speed? Number 1. The spring transfers the load the slowest. Number 2. The shock absorber transfers the load faster than the spring, but slower than the suspension link. Number 3. The suspension link transfers the load the fastest, so it is correct. Number 4. The load transfer speeds in all of the above cases are different. The load transfer speed is fastest in the suspension link, followed by the shock absorber, and finally, the spring and anti-roll bar. Therefore, the correct answer is number 3, load transfer by suspension link. Let's summarize the content of this video. In the idealized spring model, the types and parts of load transfer produced by the sprung mass can be broadly divided into two. The load transfer due to the moment produced by the sprung mass about the roll center is carried out through the spring, anti-roll bar, and shock absorber. The load transfer produced when the sprung mass acts laterally directly on the roll center is carried out through the suspension links. Most street cars have a roll center height between 50 and 200 millimeters, a roll axis angle between 6 and 12 degrees, and are designed to be low at the front and high at the rear. There is a misconception about the roll center. A low roll center means a large distance between the roll center and the sprung mass center. Consequently, the sprung mass produces a large roll moment with respect to the roll center, leading to a large load transfer. This is a misconception. Here's the truth. If the roll center is low and the roll moment is high, the load transfer due to the lateral load acting directly on the roll center is small. Conversely, if the roll center is high and the roll moment is low, the load transfer due to the lateral load acting directly on the roll center is large. Therefore, the overall load transfer does not differ significantly, and the idea that load transfer increases with the distance from the roll center to the sprung mass center is incorrect. If the distance from the roll center to the sprung mass center is large and the roll stiffness is low, the center of mass of the sprung may shift toward the outer wheel, slightly increasing load transfer. However, this is less than 3% of the total load transfer and is not significant enough to affect handling performance. There is a misconception about the roll axis. It is a misconception that a low front and high rear roll axis will cause a vehicle to understeer. Because a high roll center results in greater load transfer through the suspension links, a high rear roll center can actually lead to oversteer. Oversteer can be mitigated by increasing the vertical load on the front wheels or by adjusting the camber angle. Transient roll is explained. Roll motion with an uneven lateral acceleration is called transient roll. Transient roll occurs frequently under normal driving conditions. Transient roll and load transfer are explained. During transient roll, the forces applied to each component occur at different times. Forces are first developed in the suspension linkages, followed by the shock absorber damping force, and finally the spring and anti-roll bar. The effect of load transfer on handling is illustrated using transient turn-in as an example. Transient turn-in occurs when a vehicle enters a new road with relatively rapid steering. In a vehicle with a roll axis with a low front roll center and a high rear roll center, the force is applied first through the suspension linkage during transient turn-in, resulting in a tendency to oversteer during the initial steering stage. Next, the load is transferred largely from the side with the greater shock absorber damping force. If understeer tends to occur early in the steering process, increasing the rear shock absorber damping value can improve understeer. Next, the loads are transferred from the springs and anti-roll bars. If the front wheel roll stiffness is high, understeer tendencies may appear at the maximum load transfer of transient turn-in. If you watch the previous videos, you can learn about various fields of automotive knowledge and enjoy a more in-depth understanding of future videos. In the last video, E0080 Roll Center Part 10, I explained how to determine the location of the force roll center of a vehicle subjected to a large lateral force. I also explained the concept of the incremental roll center and its relationship to handling performance. Furthermore, I explained jacking force and that the force roll center should not induce roll motion in the sprung mass. I also explained that the position of the force roll center continuously changes depending on the magnitude of the lateral force. In the latest video, E0079 roll center part 11, I explained the migration of the force roll center. I explained the relationship between jacking force and the force roll center, and how the force roll center varies depending on the magnitude of the lateral force. I also explained how to determine the force roll center of an asymmetric suspension, and how this method can be used to find the roll center in roll motions with large lateral forces. In the next video, I'm going to explain the dive and squat associated with the pitching motion that occurs during acceleration and braking. If you found this video helpful, please hit the thumbs up and catch the brand new videos by free subscription. Also turn on alarms to be the first to see new videos. So, what are you waiting for? See you at next videos. Goodbye, guys.